In this video, we're going to take a look at Kepler's first law of planetary motion, and specifically how it may manifest in STK. Kepler's first law of planetary motion technically said planets orbit around the sun in a shape called an ellipse, with the sun at one of the two foci, which is the plural, or foci if you'd prefer, is the plural of the word focus. Now, there's a bit of terminology that we'll highlight that we'll kind of point to and use here and there, but we won't go into the fine definitions, and we'll give you an idea of how they practically apply in this. If you'd like to learn more about ellipses and Kepler's laws, you might take a look at subsequent videos or take a look at some of your math classes. All right, let's switch over to STK. All right, now what we've got here is a satellite in orbit around the Earth. Now, one of the things that I did is I set the satellite to orbit with an orbital inclination of 0 degrees. In other words, I've set up an equatorial orbit, which means the satellite's basically over the equator the entire time. Now, you don't have to do that, and you don't have to have that for what we're looking at, but it did make it nice where I can look up, and when I've got the North Pole directly beneath the camera, I know that I'm looking right down onto the orbit so we can see it clearly. Right now, by default, we have what looks to be a circle, and it is a circle. Without going into too much detail on what an ellipse is, you're welcome to check that mathematically, but it's a very mathematically specific shape. Now, for regular people, it's effectively an oval, but it's not just any oval. So the example I like to give is this. I would describe an egg being an oval shape, but it's not symmetric. One side is kind of pointier than the other. And that's something that you won't end up with an ellipse. It kind of ends up symmetric. Now, that's just a brief idea on kind of the differences between an oval and an ellipse. An ellipse is actually very precise and has a bunch of mathematical properties that go into it. Now, there are a bunch of interesting reasons, but that's the shape that all orbiting objects will actually end up in. Not just planets, but even our satellites. And so that's why it's very useful, because since the ellipse is such a mathematical shape, it actually means that there's a bunch of math that we can use to predict how that thing is going to move through its orbit. The other thing that you should be aware of is, technically, a circle is also an ellipse. You get a circle when you have the two foci, which are important parts of an ellipse, on top of each other. So this is actually a circular orbit, and in fact, when we come over here to our orbital parameters for this satellite, we've got a semi-major axis, which we'll come back to in just a moment, of 7,781 kilometers, and an eccentricity of 0. I want to highlight the eccentricity because that's actually a mathematical term for an ellipse. An eccentricity of 0 is actually when we end up with a circle. A circle is a special case of an ellipse, and it has an eccentricity of 0. So if you want a circular orbit, set your eccentricity to 0. Let's see what happens if we change that. Now we're going to make a more oval shape, something that you're a bit more familiar with. Oh, I click OK when I change my eccentricity, and it gave me a warning that, my orbit, as I've set it up, now actually hits the Earth, which generally speaking is not a great idea for our orbits, because that means that this thing is going to crash into the Earth. Okay, that's where we're going to switch over to our semi-major axis. Now, semi-major axis has a deeper mathematical definition that I'm not doing full justice, but let's just get an idea of what it does to the STK scenario. So here's what I'm going to do. We're at 7,700. Let's go up to, 10,000 instead. Apply. Oh, that's apparently not enough, but I'm getting closer. One of the things that I want to do, in fact, let's go back to an eccentricity of 0 so that you can see it a little bit better. Okay, let's get a much larger orbit. I'm going to send this thing out pretty far. Let's go 20,000 kilometers. So watch what happens when I update the semi-major axis. Our orbit gets noticeably farther out. Now our eccentricity is 0, so it is still a circular orbit. Now the semi-major axis has applications in the ellipse. In fact, that's where its definition comes from. But for our purposes, the semi-major axis can be viewed as basically how far out your satellite is. I've got it pretty far out now, so let's try an eccentricity of 0.5 like we wanted to earlier. Great. Now we've got this oval shape, but it is a specifically mathematical oval. One other thing that's very important to understand about this, the central object, be it the sun, or in many of our cases, the Earth, the thing that your satellite is orbiting, it is not in the middle of the orbit, it's at one of the two foci. In other words, what that means is as you make this more oval-shaped, more elliptical is the appropriate term, the Earth, your central object, is going to end up closer to one side. And that brings in some things that we've actually introduced in other videos. When it's the side that it's close to, this point is called the perigee, the really close point. And over here, the opposite side that is really far away is called the apogee. Now, in the next couple of videos, the other two laws, we'll see that we can actually do some interesting control of the satellite by using the apogee and perigee and by using a more elliptical orbit. Okay, well, this is 0.5. Let's check out 0.2, closer to 0. Now, this, at a glance, you might think, well, that's just a circle. It certainly looks like it, but your clue that it's not actually a perfect circle is the Earth, your central object, is not in the dead center of the circle. And so if I go down to 0.1, we're going to see it gets even closer to the center, but it's a little bit off to the side. Let's try going the opposite direction. Let's go to a highly elliptical orbit, 0.8. Uh-oh, we're crashing into the Earth again, but we can see that we've got it as a much more squished oval. Let's take this and let's send our satellite out even farther, hopefully so we're not hitting the Earth anymore. Here is a pretty large orbit. Let's see if I zoom out. There's the moon. We're nowhere near out to the moon, so we could definitely go with a larger orbit, but this is not the sort of thing that you would normally do with most regular satellites and not with our scenarios. The big thing I want to demonstrate is this, the semi-major axis, which basically controls how big your orbit is, and your eccentricity, which controls how squished, how elliptical it is. Now, an eccentricity of 0 will give you a circle with the Earth, or central object, in the middle of it, and you can go all the way up to almost 1. Now it's going to warn me because now we've got it so elliptical that it kind of crashes into the Earth again. We kind of have to increase our semi-major axis the tighter we make that oval, that ellipse. By the time you get to an eccentricity of 1, you actually shift from what's called a bound state, where you end up with an orbit that loops back in on itself. And at an eccentricity of 1, mathematically speaking, you'll end up with something called a parabola. Now, a parabola is not actually something that loops back in on itself, so you would have the satellite come in, zoom by, and go flying off. Because of how STK actually shows the orbit, I don't think I'll be actually able to show you the parabola, but let's try putting in 1 and see what it does. It doesn't like that. So, it's not a bound orbit, so STK isn't really liking that. For the most part, you want to keep your eccentricity between 0 and a little less than 1. You're probably not going to end up with a super elliptical orbit because that's going to require too big of an orbit. But this is Kepler's first law of planetary motion, or more accurately, orbital mechanics, and how it applies here in STK.